let's talk about something that's literally all around us, but we probably don't think about it that much. Matter. I mean, it's the very stuff that makes up, well, everything. Your chair, the coffee in your mug, the air you're breathing right now. So let's take a closer look at the three main faces it shows us every single day.
So let's kick things off with a little puzzle. What could an ice cube, a puddle of water, and a cloud of steam possibly have in common? I mean, they look and feel totally different, right? But believe it or not, they share a deep connection that's key to understanding our physical world. And the answer? Well, they're all just water, just wearing different outfits. And that's because they are all examples of matter. The scientific definition is actually super simple. Matter is just anything that has mass and takes up space. It's the physical stuff of the universe. Now, in our everyday lives, this matter usually shows up in one of three ways. We know them as solids, liquids, and gases. But what really makes a solid rock so different from a liquid river, or that river so different from the air? Okay, this table really lays it all out for us. You can see a solid holds its shape and its volume. A liquid, it'll flow to fit whatever container you put it in, but its volume stays the same. And a gas, well, a gas just goes wild and expands to fill any space you give it. All these different behaviors boil down to how their tiny little particles are organized and how much they like to stick together. Let's start with solids. Picture their particles like an audience in a movie theater. Everyone's got an assigned seat, they're packed in tight, and a nice, orderly pattern. Now, they can jiggle and vibrate in place, with energy, but they can't just get up and walk around. And that's exactly why a solid holds its shape. Now, in a liquid, imagine that same theater audience is now at a party. The doors to the room are closed, so nobody's leaving, that's the fixed volume, but they're not in assigned seats anymore. They can move around, slide past each other, mingle. This freedom is exactly what lets liquids flow and take the shape of a glass or a bottle. And then there are gases. Okay, picture this. That party has just moved to a gymnasium full of toddlers who've had way too much sugar. They are just zipping around everywhere, totally random, bouncing off each other, bouncing off the walls, and spreading out to fill the entire gym. There's almost no attraction between them, so they're completely free. So those analogies give us a great visual, right? But what's really going on down at that tiny, microscopic level? Why do the particles act so differently in solids, liquids, and gases? Well, it all comes down to a few basic rules that govern how they interact. So, there are basically three secrets to all these particles. First, no matter how tightly packed, there are always tiny little spaces between them. Second, they are never, ever completely still. They're always moving, vibrating, or zooming around. Scientists call this kinetic energy. And third, they have a kind of magnetic pull, a force of attraction that pulls them toward each other. So, here is the crucial point. It is all about a battle. It's this constant tug of war between the particles' energy trying to fly apart and that attractive force trying to pull them all together. And whoever wins that battle determines if you get a solid, a liquid, or a gas. If that strong attraction wins, you get a solid. If high energy wins, you get a gas. And the cool thing about this battle is that the outcome can change. Matter isn't just stuck in one state forever, it can transform. So, how do we make that happen? How do we rig the fight? Well, we've got two main tools at our disposal to influence that particle battle: temperature and pressure. When we add heat, we give the particles more of that kinetic energy, helping them break free. On the other hand, if we apply pressure, we're basically squeezing them closer together, which makes that attractive force even stronger. Think about what happens when you heat a solid, like an ice cube. Its little particles start vibrating more and more like crazy, until finally they break free from their rigid structure. That exact temperature where it all happens is called the melting point. And for ice, we all know that magic number, 0 degrees Celsius. Now, if you keep heating that liquid water, its particles get even more energy. They start moving so fast that they can finally escape from the liquid entirely and fly off as a gas. We call that temperature the boiling point. And for water, it's a nice, easy to remember 100 degrees Celsius. But sometimes matter just decides to skip a step. Some substances, when the conditions are just right, can make this amazing jump directly from being a solid to being a gas, totally bypassing the liquid phase. This is called sublimation. The best example is dry ice making all that spooky fog. That's solid carbon dioxide sublimating right into the air. And check this out, this is a perfect lab example. When you gently heat this stuff, ammonium chloride, it turns directly from a white solid powder into a vapor. Then that vapor hits the cooler part of the glass funnel and turns right back into a solid, completely skipping being a liquid. That's sublimation in action right there. Okay, let's bring all this particle science back home to something that honestly feels like a little bit of everyday magic, the cooling power of evaporation. You can think of evaporation as boiling's much quieter, more patient cousin. It's when a liquid turns into a gas, but it can happen at pretty much any temperature, not just when it's boiling. You see a puddle slowly disappearing on a cool day? Yep, that's evaporation.
So how does this work? How does it create that cooling effect? Well, for a particle in a liquid to escape and become a gas, it needs a little energy boost. And it gets that energy by stealing heat from whatever is around it. And, of course, when something loses heat, it gets cooler.
Now, this process isn't always the same speed. It happens a lot faster when it's hotter outside or when the liquid is spread out over a bigger area. A nice breeze also helps by blowing the vapor away, and it works better when the air itself is really dry or has low humidity. And this explains something we've all seen. It's exactly why your wet laundry dries so much faster on a hot, windy day. You've got the heat giving the water particles energy and the wind whisking them away. But on a cool, still, humid day, it can feel like it takes forever. You know, your own body is an absolute pro at this. When you get hot, you sweat. And as each tiny drop of that sweat evaporates, it pulls a little bit of heat away from your skin. It's your own personal, super efficient, built-in air conditioner.
And get this isn't some newfangled technology. For thousands of years, people have used these porous clay pots to keep water cool. A tiny bit of water seeps through the clay and evaporates from the outside surface, constantly pulling heat away from the water inside. It's just brilliant, low-tech air conditioning from the ancient world.
So, we've explored the 3 familiar faces of matter that really shape our world, from the solid ground beneath our feet to the very air we breathe. But it makes you wonder, what happens if you push things to the absolute extreme? What if you add so much energy that the particles themselves start to break apart? What's going on inside a star or in a bolt of lightning? It really raises the question, are these 3 states just the beginning of the story?